Okay, we should be live, just testing the audio. Okay, we're using the correct one.
Okay, settle in, everyone.
Okay, we have the audio for, and we'll be trying to stream on LinkedIn as well. So bear with me. It's trying to connect. Okay, we're not dropping any frames yet. Is it actually working? I'm not sure. It's streaming somewhere. Okay, it is streaming by the looks of it. Do I need to press another button? Ping any frames yet? Okay, we have to press go live on LinkedIn as well. Yeah, on YouTube you can do it in a few clicks, but you can automate more stuff. Okay. So should be live on LinkedIn as well. Not sure how it works. I used to do it in the past, ages ago. Yeah, I have the detail, post, repost. Should be live. Okay, that's interesting. I'm meant to be a professional streamer by now, but there's still some trouble. There is always trouble. I need to repost it. Not sure. Well, let's repost it. We have a group on LinkedIn. And see if there is any questions. So if you check the website, it's the website we developed. Hopefully, if you haven't checked it out already, go do it. Do it now. Set call for action. Yeah, we have tools around neurology. Not sure how cochlear implant, well, because it mentions the brain. Mentions the brain. And all the tools now have have this noise coming from the CPU. So I can do a noise gate to try and filter some of the noise. Because if you go, if you go fixed scale, yeah, that's what's coming from the CPU GPU. So it's going into the microphone and showing us that low frequency component. Yeah, and we can chop it off, can we? Yes. So now I don't see it. Now you do. So that's into working. Okay. What color? What's your favorite color? Ocean? Green? Sunrise? I'm not sure how this is a sunrise. It's more like a gray, brown something. Brown sunrise. Okay. And of course, obviously, we have rainbow. You can switch the array from this coil to linear. Not sure what's happening to the stream on LinkedIn. Not sure it's actually working. Not sure. Not streaming something. Okay, I'm able to add the comments. Okay, 2 people are watching. Let's just bear with me. Okay. Yeah. So let me know if there are any questions. There's probably so we revamped this tool, the Cochlear Simulator tool. We had it running on the website for a while. And yes, by the way, everything we do is available on BioniChaos.com. Go check it out. And no, this is not how I normally speak, like 2 times the speed, but I said it so many times. Go check out their site. And yes, we have some Gemini ads. And yes, we're using a lot of Gemini, so that's kind of a highly relevant ad. And now on every page you will also have a notebook LM. A notebook LM audio summary of the thing, of the, yeah, like the podcasters, the professional podcasters chatting to one another. And they're doing a pretty good job. So now we will be adding it to this interactive 3D brain mapping visualizer. For your convenience, we updated the text at the bottom, the Gemini did. And unless there are any questions, we might jump to the podcast. I'm not sure why it's a whopping 28 minutes, but yeah, let's just go for it.
Welcome to the deep dive. Get ready to explore, well, a really fascinating intersection today. Neuroanatomy, technology, and how we can make really complex stuff understandable.
We're diving into brain mapping, specifically looking at a source about a tool called Seizure Zone, interactive brain mapping for neurological understanding.
Seizure zone.
Yeah, and it offers this pretty unique way to visualize the connections between specific bits of the brain and, the functions or symptoms they might link up with.
Right. So think of this deep dive as your guided tour through the text describing seizure zone. Our mission basically is to unpack what this interactive tool is, how it does its thing, and the genuinely surprising, I think, insightful connections it helps visualize.
Connections between different parts of your brain and specific experiences or actions, sometimes quite unexpected ones, that you might see in a neurological context.
Exactly. And we'll stick strictly to what the source material tells us about it.
Right. Exploring how Seizure Zone aims to empower users, you, the listener, to build a deeper understanding of neuroanatomy and how it relates to neurological stuff using this interactive visualization as the main key.
And that's the hook, isn't it? The part that makes this, I think, both critical and fun. It's how Seizure Zone takes something incredibly complex, like the human brain and, its potential issues, and makes it visually concrete.
Mm-hmm.
It's about seeing how something that feels maybe abstract, like a particular symptom, say, a strange feeling or sudden movement, could potentially be tied to a very specific spot inside your head.
It's kind of a shortcut to grasping brain localization, but in a really engaging way, right? Without getting totally bogged down in dense medical terms.
Yeah, exactly. And we'll look at specific examples the source gives that really bring this idea to life.
Okay, so let's start with the basics. What is Seizure Zone, based just on the text we have? Fundamentally, the source describes it as an interactive 3D brain visualization tool.
Interactive 3D model. Okay, that already sounds way more engaging than just looking at flat pictures in a textbook.
It does, doesn't it?
Yeah.
And the core purpose isn't just to show you a static image. It's about letting you actively engage with a three-dimensional representation of the brain.
Okay.
The source really emphasizes its primary goal to empower users, to give them a deeper understanding of neuroanatomy and, crucially, its connection to neurological functions and symptoms.
And who are they trying to empower here? Who's it actually built for?
According to the source, it's designed with students in mind, educators too, and really anyone who's just curious about the brain. Curious minds.
So lowering the barrier to entry for neuroscience.
That seems to be the idea. Provide an accessible platform, something engaging that helps people explore these complexities. Instead of just passively reading, you can actively manipulate and look around the brain model.
Turning learning into exploration, basically.
Exactly. The central concept is this visualization. It lets you see the different brain regions, the big ones we hear about. The frontal lobe, temporal, parietal, occipital.
The major players.
Right, and it helps you understand their general roles. Like the source mentions the frontal lobe's linked to executive functions, planning, making decisions, controlling impulses, that kind of higher level stuff. Or the temporal lobe being critical for processing sounds, auditory information, and also forming memories.
Okay, so it shows the big areas and what they generally do. But how does it connect that to symptoms, to conditions? That seems like the key step.
Yeah, this is where it gets more specific. The source explicitly says the tool links these brain regions to neurological conditions, and it specifically calls out epilepsy.
Epilepsy. Okay, that makes sense as a focus.
It really does, because epilepsy often involves, abnormal electrical activity that's quite localized in the brain. And the symptoms that result, the seizure semiologies can be really clear, sometimes dramatic, examples of how messing with a specific brain area leads to observable effects.
So Seizure Zone visualizes a region and then shows how that specific area might be involved in causing certain neurological experiences, like symptoms linked to epileptic activity.
Exactly. It's about mapping the potential location of that dysfunction onto the actual physical brain structure. It connects what happens to where it might be happening.
Got it. It's not just a static map. It shows potential activity and its consequences. So how does this visualization actually happen? What's the tech underneath it all that makes Seizure Zone work, according to the source?
Okay, let's get into the technical side described in the source. The foundation is this 3D brain model. And it's not just some generic model. It's based on a widely recognized scientific standard, the Destrio Atlas.
Destrio Atlas, like a map for the brain.
Pretty much. Think of how a geographical atlas divides the world into countries, states, cities. A brain atlas, like Destrio, carves up the brain into many distinct regions based on anatomical landmarks. It gives neuroscientists a standard way to talk about specific areas.
So they're using a scientifically validated map as the base. That's important.
Absolutely. And using an atlas like this lets the tool go beyond just showing the big lobes, frontal, parietal, temporal, occipital. The source notes, it visualizes those, yes, but it also renders much more specific structures. The gyri.
Bridges, the folds on the surface.
Exactly, the prominent folds. And the sulci, those are the grooves or valleys in between the folds. These smaller details are really crucial for understanding precise localization within the lobes.
So it's a highly detailed 3D map, right down to the individual bumps and grooves. Okay, how does a user actually interact with this map
Lobes,
to
frontal,
link it up with
parietal.
symptoms?
The source describes a pretty straightforward interaction flow. The main way you explore it is by picking from a list of predefined semiology examples.
Semiology examples. So semiology is about signs and symptoms, right?
Correct. It's the medical term for studying signs and symptoms.
Yeah.
So in Seizure Zone, A semiology example isn't just one symptom in isolation. It usually represents a specific set of symptoms or clinical signs that often occur together, or that tend to point towards a particular brain area being involved.
Okay, so you pick a kind of symptom profile from a menu. What happens then?
Well, according to the source, this is where the tool's magic comes in. When you select an example from that list, the brain regions thought to be implicated or involved with that specific set of symptoms get highlighted right there on the 3D model.
Ah, okay. So you click, and the relevant part of the brain just lights up, essentially.
Yeah, it visually responds by changing its appearance on the model. That instant visual feedback, seeing the area highlight.
That must be incredibly helpful for learning. Really makes it stick.
It seems like it would be. And the source adds that alongside that dynamic highlighting, you also get a detailed description of the semiology you selected.
Ah, okay.
So you get the visual map, the highlighted brain bit, and a text explanation of the symptoms and their clinical context. It's got a multimodal approach, hitting both visual and textual learning.
Nice. The source also gives us a peek under the hood, right? At the rendering tech.
It does. It specifies that the 3D rendering is powered by the 3.js library.
3JS. Yeah, I've heard of that. It's for web-based 3D graphics.
Exactly. It's a very popular and powerful JavaScript library for doing just that, creating and showing 3D graphics right inside a standard web browser. This is a pretty significant choice, technically,
Why is that?
because it means the tool is widely accessible. You don't need specialized software. You don't need a super powerful computer. If you have a reasonably modern web browser, you should be able to use it.
Making that accessibility goal practical through the tech choice. Smart.
Absolutely. The source also mentions the underlying geometric data for the brain model is loaded using OBJ files. That's a common format for 3D shapes.
Okay.
And these files are organized and referenced through something called the JSON configuration file. Think of it like an index that tells the 3.js engine how to put together and display all the different parts of the brain model correctly.
And they use a clever visual trick, too, don't they, to make the highlights really pop?
They do. The source mentions a specific rendering technique.
Yeah.
The main overall brain model is rendered with some transparency.
Ah, so it's sort of see-through.
Yeah, a bit translucent. And this isn't just for looks. It serves a really important functional purpose. By making the main brain structure partly transparent, the highlighted regions, the areas linked to the symptoms you picked, can stand out much more clearly.
Right, otherwise they might get hidden if they're deep inside or on the other side of the model.
Precisely. The transparency helps ensure that the implicated areas are distinctly visible against the backdrop of the whole brain. It makes the key information easier to see.
That's smart design, making sure the information is the visual focus. Okay, so we've covered how it works. Now for the really interesting part, the what. What specific symptom-to-brain connections can we actually learn about from this? The source gives some pretty compelling examples, those semiologies.
Yeah, this is where that critical and fun idea really comes into play, I think. Seizure Zone presents these specific symptom sets, the semiologies, and then visually links them to the potential brain areas involved based on, established clinical understanding. And the source provides one really vivid example where it gives us both the symptoms and the specific potential brain region.
And that one is, let me see, a sense of déjà vu combined with repetitive lip-smacking movements. Okay, that's vernal. That's a combination. Déjà vu feels so internal, subjective, and lip-smacking is this outward physical thing.
It does seem like an unusual pairing if you're not familiar with seizure types, yeah. But according to the source material and the tools data, this specific combination, that feeling of déjà vu happening alongside those automatic lip-smacking movements, potentially indicates involvement of the temporal lobe.
The temporal lobe again, which we said earlier is involved in memory and hearing.
Correct, and the source actually drills down even further. It specifies which parts of the temporal lobe might be involved. The inferior and middle temporal gyri.
Inferior and middle temporal gyri. So specific ridges or folds within the temporal lobe structure itself.
Exactly.
Wow. So that feeling, that uncanny sense of I've been here before, coupled with an automatic action like lip smacking, can potentially be traced back to activity in these very specific folds on the side and underside of your temporal lobe.
That's what the tool visualizes based on the data it uses.
That connection is just fascinating. It makes the whole abstract idea of brain localization incredibly concrete, doesn't it? It's almost like finding the street address in the brain for a specific feeling and action combo.
It really is. And this example perfectly illustrates the power the source suggests a tool like Seizure Zone has. You'd select déjà vu and lip smacking. From the list, the transparent 3D brain model pops up, and then boom, those specific gyri within the temporal lobe light up clearly.
Yeah.
It transforms a, maybe dry clinical description into something you can see, an anatomical reality. And it sparks curiosity, right? Why would these two seemingly different things be linked to the same spot?
Totally. It makes you wonder how memory, perception, maybe even automatic motor stuff might all be packed together in that region.
It really gives you that visual aha moment, or aims to. Now, the source also lists several other semiology examples, but it's important to note, for these other ones, the text provided doesn't explicitly tell us the linked brain region.
Okay, that's a key distinction based on just the source text we're looking at. What are some of those other examples?
They're quite diverse, covering a real range of potential seizure symptoms. Things like visual hallucinations coupled with fear, muscle stiffening, and arm jerks.
Okay, more motor related.
Right. Then auditory hallucinations along with head turning. Sudden loss of vision combined with numbness. Just numbness, but specifically in the face and hand together.
Sensory focus there.
Yeah. Also, difficulty in speech production, so language issues, impaired coordination and balance, and even things like emotional instability mixed with autonomic dysfunction, like changes in heart rate or sweating.
Wow, that list covers a huge range. Sensory stuff, motor stuff, language, coordination, even emotions and basic body functions.
It really does. And again, while the source text itself doesn't list the specific brain areas for these, the earlier description of how the tool works tells us what would happen if you picked one.
Right. Based on the mechanism, selecting any of these examples
Would cause the relevant implicated brain regions to light up on the 3D model.
Yeah.
And you get that detailed description alongside it.
Okay, so these other examples demonstrate the breadth of symptoms the tool covers. It reinforces that it provides this symptom-to-location mapping across many different kinds of neurological events, even if we only got the specific anatomical link written out for that one déjà vu example from this source.
Exactly. It shows the tool's intended function as a kind of broad visual dictionary for seizure-related symptoms and their potential brain origins. Each one is an entry point to explore the brain's geography of function and, well, potential dysfunction.
You learn the process of mapping symptoms to regions, which seems to be the core educational goal here.
Precisely.
Now, this is clearly presented as a powerful learning tool aimed at making complex neuroscience understandable. But the source also includes a really vital section on its educational purpose and, crucially, a disclaimer. This feels important.
Extremely important. This part cannot be emphasized enough.
Yeah.
The source is absolutely crystal clear about how this tool is intended to be used. It states it's strictly for educational and informational purposes. Full stop.
It's a teaching aid, basically.
Yes, it serves as a visual aid. Nothing more, nothing less in a medical context. Its stated goal is to foster understanding, spark curiosity about brain anatomy, physiology, and how these relate to neurological conditions, again, explicitly mentioning epilepsy as the main clinical backdrop.
Right.
The developers seem to believe strongly that interactive learning, like what this tool offers, is just a better way to grasp complex subjects like the brain.
Okay, that's the purpose. And then there's the crucial disclaimer, which the source highlights pretty prominently.
Yes, and it's spelled out in bold, very clear terms. It leaves absolutely no room for misunderstanding. It says, the information and visualizations provided by Seizure Zone are not a substitute for professional medical advice, diagnosis, or treatment.
Okay, so point blank. Do not use this to figure out what's wrong with you or someone else.
Absolutely not. It goes on. This tool should not be used to make any healthcare decisions. And the final critical instruction, if you have any medical concerns or conditions, please consult a qualified healthcare professional without delay.
This really ties into the critical part of our critical and fun theme for this dive, doesn't it? It's fascinating. It's fun in an educational sense to see these connections visually.
But understanding the absolute limitations is the critical piece.
Yeah.
Self-diagnosing based on an educational tool like this would be inappropriate and, frankly, potentially harmful.
Right. So learning that, say, déjà vu and lip smacking are sometimes linked to the temporal lobe via this tool is a great educational moment. It visualizes a concept, but it's worlds away from a doctor evaluating those actual symptoms in a real person with their unique history, their full medical picture, using proper diagnostic tests.
Precisely. Brains vary between people. A generalized anatomical model, like the one based on the Destro Atlas, even though it's a scientific standard, doesn't capture your individual brain structure or situation. Real medical diagnosis is a much deeper, multifaceted process.
So this tool is like a conceptual guide, a starting point for understanding how brain regions can relate to symptoms in general.
Exactly that. It's for building general knowledge, sparking curiosity, maybe helping students visualize concepts. It is absolutely not for personal medical guidance. That prominent disclaimer is essential for responsible education in this space.
It really underscores that difference between learning general principles and applying knowledge in a specific medical situation, which needs professional expertise. Okay, shifting gears slightly, the source also tells us a bit about where seizure zone came from. It links it to a project called BioniChaos.
Yes, that's right. Seizure Zone is presented as an initiative of the BioniChaos project.
BioniChaos, interesting name.
Hmm.
Sort of biology meets complexity, chaos. What's their overall mission, according to the source?
The source describes their mission as exploring the intersections of biology, technology, and art.
Biology, technology, and art. That's quite a mix. How do those three fit together in what they're doing?
Well, their stated goal is to create innovative educational tools and also to raise awareness about complex scientific and medical topics. The source specifically highlights their focus on demystifying neuroscience and conditions like epilepsy.
Okay, so using tech and maybe art or design to make complicated science and medicine easier to grasp.
That seems to be the core idea. Leveraging technology's power, perhaps combined with the creative or communicative approaches from art and design, to make these subjects more understandable and engaging for a wider audience.
Right, and Seizure Zone fits that description perfectly then.
It really does. It's a direct example of that mission in action. It uses technology, the 3D visualization with 3.js, maybe the AI assistance for the descriptions we'll get to educate about biology, the neuroanatomy, the physiology behind the symptoms and medical topics specifically, the context of epilepsy semiology.
And the art part could be in the visualization itself, the design choices.
You could definitely argue that. The visual design, the interactive interface, that choice of rendering the brain transparently with clear highlights, there's an element of thoughtful design there, maybe even artistry, aimed at making the complex scientific information more aesthetically pleasing, clearer, and easier to absorb. It considers the user experience.
So it's not just raw data presented, it's a project that thinks about how the information is delivered and experienced by the learner.
Precisely. It seems to be about finding creative, tech-enabled ways to make dense scientific concepts approachable, engaging, and ultimately more memorable. Applying that blend of disciplines to the challenge of education.
Let's dig a bit deeper into those specific technologies and data sources mentioned. Beyond just noting 3.js, the source gives a few more details.
Right. For example, it mentions that the textual descriptions, those explanations that pop up alongside the highlighted brain regions when you select the semiology,
Yeah.
those were generated with assistance from OpenAI's GPT-4o model.
Ah, okay. So they used an AI model, a pretty advanced one, to help write the explanatory content.
Yes. And the source explains why they did that. They used GPT-4o specifically for its ability to synthesize complex neurological information and present it clearly, concisely, and in a user-friendly way.
So leveraging AI to boost clarity and accessibility, which ties back to their main goal.
Exactly. It's an interesting example of using AI not just for, say, data analysis, but actually to improve the communication and educational value of the tool itself, helping translate potentially technical medical jargon into language that students or the general public can more easily understand.
That's a really modern approach to creating educational content. Okay, what about the brain model itself?
We mentioned it's based on the Destro Atlas. The source adds a bit more detail, saying the model is derived from data that is compatible with the Destro et al. 2010 Atlas. This reference points to a specific publication, indicating they're aligning with a recognized, published standard for how the brain is partitioned.
So the map they're using is based on a specific documented scientific framework. It's not just arbitrary divisions.
Correct. It's grounded in a framework widely used in neuroimaging research. And the source is also quite explicit about acknowledging another key data source. They specifically mention and thank the resources available at brander.org.
Brander.org.
Yeah, they state that these resources were invaluable, particularly for actually obtaining the brain model data that they then adapted and used in Seizure Zone.
It's good they're transparent about where the foundational data came from, giving credit where it's due.
Absolutely. Acknowledging the creators of the atlas and the providers of the data is standard good practice, even for educational tools. And, as we noted, The source reiterates that the visualization rendering the interactive part is done in real time using 3.js.
Right, that powerful JavaScript library for Web 3D.
Yeah, repeating that point just emphasizes the smooth interactive experience. Rotating, zooming, seeing things light up instantly is all thanks to this specific web technology working right in your browser.
So when you put it all together, Seizure Zone sounds like quite a sophisticated blend. It takes standardized anatomical data from recognized sources like atlases and brander.org.
Mm-hmm.
It processes potentially complex symptom descriptions, getting help from AI like GPT-4o to make them clear.
Yep.
And then it presents these visualized connections using powerful, accessible web tech like 3JS.
It really is a multidisciplinary effort, isn't it? Which fits that BioniChaos mission biology, technology, maybe art design perfectly. It shows how you can weave together different threads of data and technology to create something new for education.
Speaking of building and improving, that leads nicely into the sources section on acknowledgments, feedback, and future plans.
Yes, they start by reiterating their gratitude, specifically thanking the creators of the Distro Atlas and the people behind the brander.org resources, recognizing the foundational work their tool builds upon.
And they seem genuinely keen on getting input from users, right?
Very much so, based on the source text.
Yeah.
It states clearly that user experience and insights are seen as vital for the tool's ongoing development. There's an explicit commitment mentioned to making Seizure Zone as effective and user-friendly as they possibly can.
So they're actually asking for feedback.
Yes, the source says they warmly welcome feedback, suggestions for new features people might want, and of course, reports of any bugs or issues someone might encounter. They also express interest in hearing how people are using Seizure Zone in classrooms, for self-study, etc.
That makes sense. That feedback loop is crucial for making any educational tool better over time, isn't it? Understanding how it lands in the real world.
Definitely. It helps the developers refine it to actually meet the needs of the learners and educators using it. It kind of turns users into collaborators in the tool's evolution.
And do they mention specific plans for where the tool might go next?
They do. The source indicates they are continuously working on enhancing Seizure Zone. It specifically mentions plans to add more detailed regional information.
So drilling down even further, maybe within the Jerry and Sulci?
Potentially, yes.
Yeah.
Getting more granular. And they also mention plans for incorporating additional interactive features, although it doesn't specify exactly what those might be in this text.
Okay, so it sounds like they view Seizure Zone not as a finished thing, but as a living project that they intend to keep improving, adding more detail and more ways to engage with it.
That's the impression the source gives, and this connects right back to you, the listener, or any user. Engaging with tools like this, providing that feedback, even just using it and perhaps uncovering areas for improvement that can directly shape its future development and make it even more useful down the line.
Okay, great. Let's try and pull all this together now for you, our listener. Why is spending time on a deep dive into something like Seizure Zone, as described in the source, particularly valuable if you're looking to, get up to speed on complex topics quickly but thoroughly without feeling totally overwhelmed?
Well, based on how the source presents it, Seizure Zone seems designed precisely for that purpose. It acts as a kind of shortcut, not by dumbing things down, but by slicing through the complexity of brain anatomy and how it correlates with symptoms, using that powerful tool. Visualization. It takes something incredibly intricate, the 3D structure of the brain, how specific symptoms might map onto it, and makes that connection direct, visual, and hopefully more intuitive.
And that visual element is the real game changer compared to just, say, reading a list, isn't it? It's one thing to read temporal lobe, it's another to actually see it light up when you explore déjà vu and lip smacking. It builds a kind of spatial understanding.
Exactly. It aims to make that abstract idea of brain localization tangible, immediate. And this is where that critical and fun aspect really shines, I think. It makes learning about the brain genuinely engaging, maybe even captivating, by highlighting these specific, sometimes quite surprising, connections.
Yeah, that déjà vu example keeps coming back because it's so concrete.
It is. It's specific, it's a bit unexpected, and seeing where it potentially maps in the brain just makes the information stick differently. It's designed to give you that aha moment, visually delivered.
It absolutely seems like a way to quickly gain solid, memorable knowledge about specific brain symptom relationships, which fits perfectly if you want to be well-informed efficiently. You could use it to look up symptoms you've heard about or are curious about and immediately see the potential anatomical link, according to the tools model.
And beyond just the brain facts you might learn, it's also a fantastic case study in itself. It shows how these diverse modern elements, detailed anatomical data, advanced 3D web technology, sophisticated AI helping with clear communication, and a real focus on user experience are all being woven together.
To create entirely new ways to learn.
Yeah, new accessible ways to learn about complex biological systems like our own bodies. It really demonstrates the potential for technology to make subjects that might seem daunting or intimidating much more approachable and interactive for everyone.
You can really picture spending time with a tool like this and developing a much stronger, more intuitive feel for brain geography and how different areas connect to different experiences than you might ever get from just staring at static 2D diagrams in a book.
It shifts learning from passive reception to active exploration. It's positioned as a tool for discovery.
Okay, so wrapping up this deep dive into the Seizure Zone tool, based purely on our source material, we've seen how this interactive platform, built on scientific atlases and powered by modern web tech and AI, aims to offer a unique visual pathway into the complex links between brain structure and neurological experiences.
It makes that connection, say, between a symptom profile like deja vu and lip smacking and a specific spot like the temporal lobe tangible and hopefully much more understandable for learners.
Yeah.
We really try to highlight how functions and dysfunctions can be localized in the brain.
It's a clear example of trying to visually map clinical observations onto the underlying neuroanatomy, all for educational purposes. And maybe here's a final thought to leave you with, something to chew on after this discussion. We've explored how Seizure Zone helps visualize these specific, sometimes seemingly unrelated symptoms like deja vu and lip smacking, potentially pointing to the exact same brain area, the temporal lobe in that case. This ability to map precise experiences to precise locations is only growing stronger with technology.
It is.
So, what does this increasing capacity to anatomically locate, to visualize the where of very specific, very personal thoughts, feelings, or actions as tools like Seizure Zone demonstrate is possible, at least conceptually, what does that tell us about the future potential for understanding and maybe, just maybe, one day influencing the most specific and personal aspects of our own internal lives? If a specific feeling like deja vu or maybe even a complex emotional state has something like a visible zip code in the brain that we can pinpoint, what are the deeper implications for how we understand consciousness, identity, experience itself?
That's a profound question, isn't it? About mapping the material basis of our subjective reality. Lots to think about there.
Yeah, there is a human in the loop. If you have any questions, more than happy to answer them. We had like a comment on YouTube, but not sure what to do with it. Probably ignore. Meant to be funny, but not really. And also, yeah, we had a comment from Manura on LinkedIn. So is there any testing that needs to go through for ethical approval? Okay, someone is deep into applying for ethics applications. Or is it just ready to be used in practice? Yes, so we have to be clear on that one. This is synthetic data. Not sure it mentions so the semiology examples. So essentially this text is generated by ChatGPT 4, and we actually might go over them and potentially try and improve this data set. But yes, it's a synthetic data set, so in theory, pretty sure, correct me if I'm wrong, but there should be no ethical approval concerns whatsoever, because we're using synthetic data. And here are professional podcasters addressing this question as well for your convenience.
So you sent over the source material for this Seizure Zone app, And yeah, that initial reaction, yeah, wait, is this all synthetic data? Is it all AI generated? Totally understandable.
It really is. You see AI mentioned, and that's often the first thought.
Exactly. And that specific question is perfect for what we do here. Let's really unpack it.
Yeah, because that's the core mission for this deep dive, right? To figure out the different places the data in this application actually comes from. Because you're right, it's not just one thing.
It's not a simple yes or no. So we're going to look at what the source material says is AI and what actually comes from, established science.
Okay, so let's start with the most direct part. The source is pretty clear about where the AI comes in. It says the textual descriptions were generated with the assistance of OpenAI's GPT-4o model.
Okay, wow. So the actual words, the descriptions of the seizure symptoms, like when it mentions deja vu or those lip-smacking things for the temporal lobe, that text itself is AI written. The source says the aim was, what? To synthesize and present complex neurological information in a clear and user-friendly manner.
Exactly. So it sounds like AI's job here is clarity, making complex stuff easier to digest.
Right, for accessibility, not
Oh, yeah.
generating the fundamental information itself.
Precisely. The AI is the translator, in a
Wow.
way, making the medical jargon more understandable. And this is the key distinction we need to make the underlying brain model, the 3D thing you actually interact with.
Yeah.
That's fundamentally different. The source is very explicit that anatomical model is not synthetic. It wasn't just, imagined by an AI.
Okay, so the AI didn't just dream up a brain structure.
No, definitely not. It states that the model is based on the widely recognized Destro Atlas.
Ah, okay, I've heard of that. That's a standard map, right? Used in neuroscience research.
A very standard one. For mapping brain regions, the source even mentions the data came from places like brander.org, standard geometry files. So the foundation, the actual map of the brain, that's built on established scientific data.
Right, not AI creation. Okay, that's a critical difference. So map equals science. Text on the map equals AI for clarity. What about the specific examples, though? Like the points it shows for visual hallucinations or muscle stiffening. Did the AI just invent those concepts too?
Well, the source called these examples real clinical concepts. So they're meant to be predefined examples of symptoms tied to certain brain areas based on, clinical understanding.
So the concept is real, rooted in medicine, and the AI just writes the little blurb about it.
That seems to be the setup. It aligns with the tool's stated purpose, which the source mentions is about fostering understanding and curiosity about the brain and epilepsy, trying to demystify it all.
Demystify neuroscience. Yeah, okay, so it sounds like they're layering things. You've got the scientific base, the clinical ideas, and then the AI text to make it approachable.
Exactly right. A scientific atlas provides the structure, clinical knowledge informs the examples, and AI generates the accessible descriptions. It's a blend.
Okay, that clarifies things a lot.
Yeah.
So definitely not all synthetic. It's a mix. The brain structure is scientific data, the examples are based on clinical concepts, and the AI handles the explanatory text.
And it's really important to remember what the source stresses. This whole thing is educational.
Right, the disclaimer.
Yeah, the big disclaimer, not a substitute for professional medical advice. The AI part is there to help people learn to make complex, science-based info easier to grasp.
Look at seizure zone sources. It really highlights something broader about information tools today, doesn't it? This blending of data origins. You've got AI-generated stuff sitting right next to data pulled from, decades of scientific research.
It's becoming more and more common.
So thinking about this specific mix, the scientific data for the brain model, the AI for the easy-to-read descriptions, what does that make you, the listener? Think about all the different layers of information you run into every day. How much do we really know about where each piece comes from and why that origin story matters?
That's a great takeaway thought. Every bit of information, whether it's text or a 3D model like this, it has an origin science, AI processing, human curation, something else. Understanding those layers, where they come from, it really shapes how we interpret things, especially complex topics. Definitely something to keep in mind as you navigate, everything out there.
So there's a human in the loop. If you have any questions, go for it. Show what's happening to the LinkedIn stream. Doesn't look very healthy. Cannot make comments. And I think I have to like keep refreshing the page or something. Yeah, link that's pretty bad. It's like really bad. Well, at least the streaming is. So if there's any other questions. That's the original data source that we generated. And as if you haven't checked, everything we do is eventually available on BioniChaos.com. Go check it out. Yeah, we have this EEG signal simulator as well that you might like. Yeah, I would actually like to test it on another browser. So say this advanced signal generator. Yeah, the styling there for the page took some time to load. But that's okay. And we have this audio, the Notebook LM audio on each page. I think I played this one before, but well, I need a reminder as well. So
welcome to a new deep dive. Today we're plunging into the fascinating world of brain signals.
Yeah, and we're using a source that describes a specific tool, an advanced EEG signal simulator.
Okay, so let's unpack this then. What's our goal here? What are we trying to figure out?
Well, the mission is really to get a handle on what these EEG signals actually are, how they're, put together from their basic parts.
And what gets in the way, like noise and stuff.
Exactly. Interference. What messes up clean recordings. And critically, how a tool like this simulator we're looking at helps us learn about these really complex waveforms.
Because, I mean, think about it. Our brains are constantly going all this electrical activity.
Non-stop.
And being able to measure that, understand it, that seems absolutely key for insights into like different cognitive states, right? Or diagnosing neurological problems.
Or even just grasping general brain function on a deeper level. It's fundamental.
Right.
And that's really where a simulator like the one in our source comes into play. It lets us generate a synthetic signal.
Synthetic, like artificial.
Yeah. Basically an artificially created waveform, but one that mimics the characteristics of real brain activity.
How does it do that?
Well, the source explains it lets you combine the fundamental brain waves, delta, theta, alpha, beta, and then, crucially, it lets you add in common types of noise, artifacts, they call them.
Artifacts. Okay, so instead of just getting this like messy real-world recording,
which can be really chaotic,
this tool lets you build the signal piece by piece. See the components.
Exactly. You can isolate things, see how they interact. So, whether you're just curious about this stuff or maybe you need to get the basics down quickly.
This deep dive should give you that foundation.
Right. And what's really interesting, as the source points out, is how this kind of tool serves, well, two main groups. For someone new to EEG, it's like an intuitive playground. You tweak things, see the results instantly, helps build that gut feeling for how it works.
Makes sense. Learn by doing.
But then for someone more experienced, maybe, say, an engineer developing signal processing algorithms, it's a reliable utility.
How so?
Because you have this controllable, predictable signal, you know exactly what went into it, so you can test your algorithms maybe for filtering out that noise we mentioned, or even for developing brain-computer interfaces.
Gotcha. A controlled test bed. So, based on the source, how is this thing actually structured? How does it work?
So it describes the application as being split, basically. Control panels on one side, where you set everything up, configure the signal,
Okay.
and visualizations on the other side, where you see the results. You change something in the controls.
And the graphs update immediately.
Dynamically, yeah. So on that control side, there are a few key sections that really help illustrate how we characterize brain signals. First, brain state presets.
Presets, like pre-configured settings.
Exactly. And this is super helpful because, as the source notes, different mental states tend to correlate with different patterns of brainwaves.
Oh, right. Like being relaxed versus focused.
Precisely. So you might select relaxed meditative, and the simulator automatically boosts the alpha wave amplitude that's typically strong, around 8 to 12 hertz when you're relaxed but awake. It's a quick way to see a representative signal for a known state.
Ah. Okay, so you don't have to manually guess what a relaxed brain signal looks like. It shows you a typical composition. That's pretty smart.
It really helps connect the states to the signals. And then there's the artifact simulation section. This is so important.
Why is that?
Because, and the source really emphasizes this, real-world EEG is almost always contaminated. You get electrical signals that aren't actually coming from the brain itself.
Right, like muscle movements.
Exactly. The simulator lets you dial in common ones. You can add muscle artifact, that's EMG signal. It shows up as high-frequency noise, kind of spiky, from things like clenching your jaw or even just scalp muscle tension.
Yeah, the source mentions those look like really fast, messy spikes in the data.
Oh, they can totally swamp the brain signals you're trying to see. And then there's eye blink artifact EOG. That shows up differently.
How so?
As large, slow wave spikes, usually below like 1 hertz. It happens because your eye itself has an electrical charge, a dipole, and when you blink, it moves, creating this big voltage shift.
Wow. So being able to simulate these, it really drives home why cleaning up real EEG data is such a big deal. You have to get rid of this stuff first.
Absolutely. It makes you appreciate just how complex those real recordings are and why signal processing is essential.
Okay, so beyond presets and artifacts, what else can you control?
Well, then you have the fine-tune waves control panel. This is where you get really granular. You can adjust the fundamental brainwave components individually.
The delta, theta, alpha, beta waves.
Yep, delta, usually 0.5 to 4 hertz, deep sleep territory. Theta, 4 to 8 hertz, think drowsiness, light sleep, sometimes creativity. Alpha, 8 to 12 hertz, that relaxed wakefulness we mentioned. And beta, 13 to 30 hertz for active thinking, being alert, focused.
And you can just adjust sliders for these.
There's a simple mode, yeah, with sliders to quickly change the relative strength, the amplitude of each band. Easy way to play around.
But the source mentioned a customized mode, too, for digging deeper.
Exactly. In customized mode, you can get really specific. You can set the precise center frequency for a waveband.
Okay.
The bandwidth, like how spread out the frequencies are around that center point, and of course, the amplitude or power for each one.
So you could try and replicate specific findings from a research paper or something.
Precisely. Or just explore how changing just one parameter, like bandwidth, affects the overall look of the signal in its spectrum. Very powerful for understanding the building blocks.
And there was something about spectrum overlays mentioned in the control section, dotted lines.
Right. Those show up on the power spectrum graph, which we'll get to. These overlays represent the sort of theoretical ideal shape of each pure brainwave band you've configured, like the raw ingredient before mixing.
Okay, like the ideal alpha shape, the ideal beta shape.
Exactly. Which leads us nicely into the visualization side. 2 main graphs are presented in the source.
Right.
First, the power spectrum. This one's shown in the frequency domain.
Frequency domain, meaning it shows frequencies, not time.
Correct. It's generated by applying a mathematical tool called a fast Fourier transform, an FFT, to the raw signal. Think of the FFT as deconstructing the complex signal that changes over time and showing you how much energy or power is packed into each specific frequency. So you see peaks where your dominant brainwaves are. It's absolutely crucial for seeing the underlying frequency components.
Got it. So it tells you what frequencies are strongest in the mix and the other graph.
That's the simulated EEG waveform. This one is in the time domain. It shows the raw composite signal, the voltage just fluctuating up and down over time, typically over like a 5-second window, the source says.
Ah, so that's the trace that looks like the classic brainwave recording.
Exactly. And it's
In-
literally the sum of everything you've added, all the individual brainwaves plus any artifacts you dialed in. It's the final mixed signal.
Okay. Now, here's something the source really flag is important. You mentioned those dotted ideal overlays on the power spectrum graph. And then there's the actual computed spectrum, the filled-in blue area from the final mixed signal. The source says they don't line up perfectly, right? Even if you only have one main wave active.
Right. And that's not a glitch. It's actually a really key concept the simulator helps illustrate visually. It's fundamental to how waves work.
Okay, so why don't they match? Why isn't the final spectrum just a perfect stack of those ideal shapes?
It comes down to interference. The source uses a great analogy. Think of that final blue spectrum, the one computed from the waveform, as a cocktail.
A cocktail.
It's made by mixing all your ingredients, delta, theta, alpha, beta, plus any EMG or EOG noise you added. Those dotted overlays, though, they're like looking at one pure ingredient in isolation before it got mixed into the drink.
Okay, I like that. The cocktail analogy works. Things blend. They don't just sit there separately.
Precisely. When you add waves together in the time domain to create that single up and down waveform trace, they interfere with each other, constantly. At some points in time, the peaks of different waves might line up. They add together, making a bigger peak. That's constructive interference.
Okay, adding up.
But at other moments, a peak from one wave might align with a trough, a dip from another wave. They partially cancel each other out. That's destructive interference.
Ah, okay, so this adding and subtracting is happening all the time along the waveform.
All the time across the entire signal. So when you then take that final combined interfered with waveform and run the FFT on it to see its frequency components.
The result isn't just those neat ideal curves stacked up.
Exactly. The resulting power spectrum, that blue area, is more complex. It's, lumpy, as the source describes it. It reflects how those pure components actually interacted over time to create the final signal you see.
So the overlays show the ideal ingredients, but the blue area shows the actual cocktail after mixing and interaction.
Perfectly put. The overlays are still super useful. They guide your eye, showing you where the energy should be concentrated based on your settings. But the blue area is the reality of the combined signal's frequency content. The simulator makes this relationship much, much more intuitive.
Yeah, you can see it directly instead of just imagining equations. It shows why the sum of the parts looks different in the frequency domain compared to the time domain.
It really demystifies that link between the raw signal and its frequency breakdown.
Okay, so let's wrap this part up. What does this all mean? We've taken this deep dive into the EEG signal simulator. We understand its purpose education, algorithm testing.
Right, we looked at its parts. The brain state presets for typical patterns, the artifact simulation is super important for understanding real-world challenges like muscle noise, EMG, and eye blinks, EOG.
And the fine-tuning controls.
Mm-hmm.
Simple sliders, but also that customized mode for setting specific frequency, bandwidth, amplitude for each wave, delta, theta, alpha, beta.
Then the visualizations, the power spectrum, using the FFT to show power per frequency. That's the frequency domain view.
And the simulated EEG waveform, the raw signal over time, the time domain view.
And we really hit that key concept why the actual signal spectrum, that blue area, looks different from the ideal overlays.
Right, it's all about signal interference. Constructive and destructive interaction between the waves in the time domain.
Meaning the final frequency breakdown isn't just a simple sum of ideal shapes, it's more complex, like that cocktail analogy. Seeing that visually is a huge takeaway.
Absolutely. And the source also touched on future ideas for a tool like this.
Yeah, some exciting directions. Adding more waveforms like gamma waves, those faster frequencies above 30 hertz, often linked to higher cognitive stuff.
Okay.
Simulating more artifact types, maybe EKG from the heart, or that annoying 50 or 60 hertz hum from power lines.
Oh yeah, that hum gets everywhere.
Definitely. Also, more advanced analysis like spectrograms, which show how the frequency spectrum changes over time. Multi-channel simulation to look at patterns across different scalp locations.
So simulating a whole head of electrodes.
Potentially, yeah. And even maybe importing real-time data. Lots of possibilities.
So ultimately, this simulator, as the source presents it, it's this dynamic learning tool for newcomers, right? But also a practical utility for people already in the field.
Exactly. It makes the complexities of EEG, which can seem pretty daunting, much more intuitive and interactive. It helps bridge that gap between the raw squiggly lines you record and the frequency information hidden inside them.
By letting you build it up yourself and see the connections.
Precisely. It demystifies that relationship.
Which actually leads to a pretty important question to leave you, the listener, with.
Okay.
Given how dramatically these artifacts and just the natural interaction between different brain waves can change the signal we actually see, change it from those clean, ideal components.
Yeah, in ways we can't always project perfectly in real life.
Right. So how might that reality influence how we interpret real clinical EEG recordings, where we don't have the luxury of knowing the exact ingredients that went in?
Good question.
And what does that imply for building tools like brain-computer interfaces that need to be really robust and accurate? How do they deal with all that inherent noise and complex interaction to reliably figure out what the brain is actually doing?
Okay. Yes, all these tools are on BioniChaos.com. Go check them out. Let me know what you think. Any feedback will be used as prompts to AI. So as you can imagine, it's all developed by AI. And there is a human in the loop. If you have any questions, go for it.
Hey there, and welcome back to the Deep Dive.
Great to be here.
This is where we grab a whole bunch of sources, stuff people send in, research, articles, and we really dig in.
Try and pull out the key stuff, the interesting bits.
Exactly. Get you informed, find those connections, maybe, spark some ideas. So today, we're diving into something pretty amazing, actually. We're exploring how specific neurological symptoms, things patients actually experience, might link up directly to identifiable spots in the brain.
Yeah, it's like using symptoms as breadcrumbs almost, following them back to the source.
Right. Not just problems, but actual clues.
And the sources we have today are fascinating. They detail different symptoms and then pinpoint potential brain areas involved in each case. It's almost like mapping the brain's functions based on what goes wrong, or differently.
Totally. So our mission, let's say, is to unpack these links.
Yep.
Try to get a feel for what these different brain bits might be doing, and see how these symptoms really can unlock secrets about, well, the brain's layout.
The geography of function, you could say?
I like that. Okay, let's unpack this. So we'll work through the source material, looking at these different symptom sets and where the sources suggest they originate.
Sounds good.
Let's kick off with something, maybe a bit eerie. A patient experiencing a strong sense of déjà vu.
Ah, that feeling, like you've absolutely been there, done that, even though you know you haven't.
Exactly, that sort of inappropriate familiarity.
Right, so the source connects this, especially when it happens alongside things like repetitive lip smacking, automatic movements.
Okay.
It links that to the temporal lobe.
The temporal lobe. And it gets specific, right? It mentions the inferior temporal gyrus and the middle temporal gyrus. Just quickly, for anyone picturing it, a gyrus is like a ridge on the brain's surface.
Yeah, one of the folds.
Uh-huh.
And a sulcus is the groove in between.
Got it. So the temporal lobe, why there for déjà vu and lip smacking?
Well, the temporal lobe is huge for processing senses, forming memories, retrieving memories, and also some of these automatic behaviors.
Ah.
So that feeling of weird familiarity or automatic stuff like lip smacking, it really fits with unusual activity or maybe some disruption in that zone.
So it's not just storing memory, but generating the feeling of memory.
Precisely. That subjective sense of, I know this, even when it's wrong, that's what this symptom kind of highlights about those specific jiri.
Wow. Okay, moving to a different kind of experience. This one's quite dramatic. Seeing visual hallucinations.
Seeing things that aren't there.
Yeah, and at the same time, getting hit with sudden, intense fear.
Oof, that's a powerful combination.
Right. So where do the sources point for that?
Well, it suggests two distinct but crucially interconnected areas. The visual hallucinations naturally point towards the brain's visual processing center. That's the occipital lobe at the back.
Okay, occipital lobe for vision makes sense.
And the intense fear, that points straight to the amygdala.
The amygdala deep inside. And the source even names specifics in the occipital lobe, like the middle occipital and lenatus sulcus. And the anterior occipital sulcus, and then, yeah, the amygdala.
And this is where it gets really interesting, like you said.
Yeah.
Because you've got sensory distortion from one area, the occipital lobe, and this raw emotional response from the amygdala happening together.
It shows they're linked somehow.
Exactly. It highlights that these aren't isolated systems. Sensory input and emotional response are deeply tied, and a symptom like this reveals that network in action, or maybe misfiring together.
It's like the patient's experience shines a spotlight on that connection.
Perfectly put. It illuminates how different regions collaborate to create these complex subjective states.
Okay, let's switch gears to movement. Next up, a patient with tonic muscle stiffening.
Like going rigid.
Yeah, followed by rhythmic jerking in the arms. Sounds very motor-related.
Absolutely. Symptoms like that strongly suggest something's going on with the motor cortex, the brain's command center for voluntary movement.
And the source flags the precentral gyrus.
That's the one. And also the inferior precentral sulcus.
The precentral gyrus. That's the main strip for motor control.
Essentially, yes. It's where the signals to move your muscles voluntarily kick off. So if there's, say, abnormal electrical activity there, you get these uncontrolled outputs, the stiffening, the jerking.
So the symptom confirms its job, basically.
In a very direct way, yeah. It shows what happens when that control signal goes haywire.
Okay, let's look at another perception-related one, but auditory this time. A patient hearing voices or sounds that aren't there.
Auditory hallucinations.
Followed by involuntary head turning.
Right. So hearing things that aren't real points towards the auditory processing areas. And those are mainly located, again, in the temporal lobe.
Ah, back to the temporal lobe. Interesting. It seems to do a lot.
It really does. But different parts handle different things. Here, the source mentions the planum polare.
Okay.
And look, the middle temporal gyrus again.
The same one mentioned with déjà vu.
Yeah, which is fascinating, right? It suggests maybe different kinds of activity in the same broad area or slightly different circuits involving that gyrus.
Or different networks connecting through it.
Could be. This symptom points more to the auditory processing function within that lobe and the head turning. Maybe a reflex, like trying to locate the source of a sound that isn't actually there.
So it shows specialization within the temporal lobe, different neighborhoods, like you said before.
Exactly. Auditory processing here, memory and familiarity over there, even if they're geographically close.
Got it. Okay, now this one sounds complex. Sudden loss of vision in one eye.
Okay, visual loss.
Followed by numbness down one whole side of the body.
Whoa. Okay, yeah, that's another great example of symptoms pointing to multiple distinct brain areas.
So vision loss points where? Back to the occipital lobe.
You got it. That's the visual processing hub. And the numbness, the loss of touch sensation down one side, that points to the parietal lobe.
Parietal lobe that handles touch and body sensation.
Touch, temperature, pain, proprioception, knowing where your body is in space.
And the specifics mentioned are the middle occipital gyrus again, and the primary visual cortex for vision, and the intraparietal and parietal transverse sulcus for the sensory part.
And what this really drives home is how the brain processes different senses in different places. Vision in the occipital, touch in the parietal. Even though both are about losing sensation, they map to different zones based on the type of sensation.
Parallel processing pathways.
Exactly. This symptom set really highlights that division of labor.
Okay, following on from numbness, what if it's more specific, like numbness just on one side of the face and in the hand on that same side?
That's different from the whole side numbness. More localized.
Yeah, So what does that suggest?
That points very specifically to the primary somatosensory cortex. That's the main receiving area for touch and body sensations, located in the parietal lobe.
And the source mentions the postcentral gyrus and the superior parietal lobule.
Right. The postcentral gyrus is key here. Think of it like a map of the body laid out across the brain surface.
A sensory map.
Exactly. And some body parts, like the face and hands, have disproportionately large areas dedicated to them on that map because they're so sensitive.
So if the numbness is just face and hand, it strongly suggests the issue is limited to those specific patches of real estate on the postcentral gyrus map.
That's incredible. So the symptom's location on the body tells you the location in the brain.
It's a beautiful example of that somatotopic organization, much more fine-grained than the whole body side numbness we just talked about.
Wild. Okay, next one. Difficulty producing speech. Not understanding, but actually speaking.
Classic symptom. This immediately makes you think about the frontal lobe, specifically an area famous for language production.
Which the source identifies using terms like pars opercularis and pars triangularis, which are parts of Broca's area.
Right, exactly. Broca's area is crucial for the motor planning and execution of speech, getting the words out, forming the sentences smoothly.
So someone might know what they want to say, but struggle to articulate it?
Precisely. It highlights how even something as complex as fluent speech relies on specific motor programming regions in the brain. Okay, let's shift slightly. What about problems with coordination and balance? Feeling clumsy, unsteady.
That symptom profile points strongly towards the cerebellum.
The cerebellum, okay, that's at the back, underneath the main brain lobes.
That's right, tucked away back there. Now, the source also mentions the superior parietal lobule and the angular gyrus.
Which are in the parietal lobe. We heard about the superior parietal lobule with the localized numbness.
Right, and those parietal areas are involved in spatial awareness and integrating sensory information, which is definitely important for guiding movement. But the cerebellum is really the main coordinator.
That's smoothing things out.
Yeah, fine-tuning voluntary movements, maintaining posture, balance, making everything work together fluidly. So impaired coordination, poor balance, that's classic cerebellum territory, even if other areas contribute inputs.
Got it. Cerebellum for coordination. Okay, last set of symptoms from our sources. This one's about emotional instability combined with autonomic dysfunction.
Autonomic dysfunction, so issues with automatic body processes.
Yeah, like heart rate, breathing, digestion, stuff that just happens without conscious thought.
Right, so big emotional swings, plus problems with those basic bodily functions. That combination points towards brain regions involved in regulating our internal world, both conscious feelings and unconscious processes.
And the areas named are the cingulate gyrus and the insular cortex. Not areas you hear about every day, maybe.
Perhaps not as much as, say, the motor cortex, but absolutely crucial. The cingulate gyrus is a big part of the limbic system. Think emotion processing, motivation, regulating behavior.
Okay. And the insular?
The insular cortex, or just insula, is fascinating. It's kind of tucked away deep in the brain. It's a major hub for interoception.
Interoception, meaning?
Sensing your own internal bodily state, feeling your heartbeat, your gut feelings, hunger, thirst, the need to breathe. It integrates all that internal sensory data with your emotions and thoughts.
Wow. So if those areas are affected.
You can see how it could lead to both emotional instability because the ocean regulation circuits are disrupted and autonomic problems because the areas monitoring and helping to control those internal body states aren't functioning properly.
It connects the physical feeling inside with the emotion.
Gnarly! These symptoms really reveal the brain's role in linking our internal physical reality with our subjective emotional experience.
Incredible. So we've gone all the way from déjà vu,
Lip smacking,
visual and auditory hallucinations, motor problems, speech difficulty, balance issues,
numbness, localized and widespread.
and finally, this link between emotion and our basic body functions. Each symptom, like you said, acting like a little pointer to specific gyri, sulci lobes.
Different spots on the map.
So what does this all mean? Where does this leave us? Well, I mean, what we've really unpacked here is just how powerful symptoms can be as clues. Looking closely at what someone experiences subjectively can point us towards which parts of the brain might be involved and what those parts normally do.
It's like building that functional map, not just by looking at anatomy, but by seeing what happens when specific bits are, let's say, acting up.
Yeah, using the malfunctions to understand the function.
Right. But it's also really important to remember, while these symptoms can point to specific regions, a gyrus here, a sulcus there, The brain works as a massive interconnected network.
It's not just isolated spots.
Definitely not. Often, a symptom is really about a disruption in the communication between areas that usually work together. So understanding the role of individual spots is crucial, absolutely. But the bigger picture is always about how they all interact and connect.
That makes sense. The network is key. Still, it's pretty mind-blowing how specific functions seem to map onto specific structures.
It is. It's testament to the brain's incredible organization.
And it leaves us with, I think, a really cool thought to chew on.
Mm-hmm.
Next time you experience something really simple, feeling the warmth of the sun on your skin, tasting something bitter, hearing a familiar voice, maybe even just that weird flash of déjà vu, just pause and consider that experience. It isn't just happening vaguely in your head. It's happening because specific named parts of your brain structures, like the postcentral gyrus processing that touch, or the insula registering that internal feeling, or the temporal lobe sparking that sense of familiarity, are physically active, firing, doing their job right then.
The physical basis of subjective experience.
Exactly. So what does that incredibly direct link between the physical stuff inside your skull and your entire felt experience of being alive make you wonder about consciousness, about what it means to be you?
A deep question indeed.
Something to ponder. We hope this deep dive into symptoms and brain geography has given you maybe a new angle to think about things.
Keep exploring, keep questioning.
Absolutely.
Oh.
We'll catch you on the next dive.
Yay. So there's a human in the loop. If you have any questions, complaints, go for it. Go for it. Go for your life. Colors. You don't like the colors. That's normally what people complain about, but why my CPU is doing extra. This tab is only 270 megabytes. And there's a question. What is that? Just see this now. That's a cool question on YouTube. Not sure what's happening to the stream on LinkedIn. I think it's there's either like a technical issue. Yeah, LinkedIn is not great. Or the algorithm doesn't like it, let's say. And there's a question. Oops. To mute the tabs. It's the LinkedIn tab. Have to mute it. It's the question. Have you an emotive or Neuralink or something? I don't have context. LOL. 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 Do you have a Neuralink? Do you have a Neuralink? It could be an interesting simulation, wouldn't it? Get your brain hammered. Get your brain hammered with a Neuralink device. Let's flex some muscle for you. Oops. And we did this one as well. Did I share it? No. Let's say. Oh, the language. Yeah, that's why. LLM is your friend, so I can actually understand what you're saying. Something about purchasing and a motive. Yeah. Okay. Yeah, I wouldn't waste my money on the motive. Yes, what did we cover? What did we cover? Ah, this one's... No, we do... Anyway, all of those are in the production. You can go check them out on BioniChaos.com. Everything we do on this channel eventually appears on this website for you to play with. So go check it out and let us know what you think. But yeah, I don't think there's much point commenting before checking the website out. And yes, we have a lot more in development. Well, as if this should be enough for most use cases. Even have a Boyd. Why is it? Wait. Yeah, this kind of stuff meant to be at the very bottom of the page, but there is... Can add some music to it. What would be a good music for this one? Music effects. Does this even work? Because it didn't work yesterday. I don't think it works. Generate. No, something went wrong. So I think music effects is down, but music effects DJ is still working. No, we don't want our performance. Let's start with a piano ballad. Sharks with lasers. What's that? Cohesion. Cohesion button. Where did you see the cohesion button? Oops. Cohesion button. Yeah, there should be cohesion meant to do something. Yeah, they're doing this. So this is based on a paper back from forever ago. Should be a link on the page. Yeah, paper back from 1987. How good is that? I think it's, yeah, 1987 Boyd's. Yeah, this bird simulation stuff. So the cohesion must have been mentioned in the original paper. Must have been mentioned in the original paper. Yeah, and that's the running simulations. You can change the counts. The original one of the bots did it. It was like re-rendering the whole canvas. But now it's actually adding and removing the Boyds. They're called Boyds. It's a good name. And yes, cohesion does that kind of stuff. It can increase the speed. We can match the speed to the music. Alignment. You know, they look like a bit lost. Okay, let's keep them. Most of the time the middle of the controller should be fine. And yes, this simulation is deployed on the side, so you can check it out yourself. Let's put everything at around 50%. Yeah, if you add a bird, no predators or food, we have other simulations. We have a lot of like game stuff. Games are good. I don't know, people were complaining, oh, this biomedical engineering website with a biomedical data science website, and why do you have games on it? Yeah, games are actually really good that way, because you can test your prompts and benchmark the LLM that you are using. So they are really good that way, because you can give it to whatever. Currently I'm on Gemini, but give it to any AI, generate prompt, standalone prompt for a senior developer, and it will actually do it for you. How good is that? And then you can test how well the LLM, whatever currently I'm using, what am I using? We have access to Claude 3.5, 3.7, 3.7 thinking, Sonnet 4, Gemini 2.0 Flash, 2.5 Pro, GPT 4.1. I thought it's not a thing anymore. 4.0 is the good old 4.0, nice and quick. Or one preview, yeah, everything that's indicates by preview it's probably not working properly. 3 mini, 4 mini preview. So in the GPT, in OpenAI, in the ChatGPT on the website, they have 4 mini high. That was actually quite good. Anyway, so in this case, it seemed to know everything on procedural animation. What's they call? GPT just use it to unlock my what? Yeah. We are not going there. You can unlock anything you like. If you ask it the correct question. Okay, this music is a bit annoying. What's Mellotron? What on earth is Mellotron? Shark with lasers. Have to try that one. Sharks with lasers. Ooh, that's annoying. Chill out. Yeah, we need to chill out. That's for sure. We need more chilling out to do. I think my LinkedIn stream is dead or something. Not sure what happened to it. Not sure what happened to the LinkedIn stream. Just keep the chilling out bit. Okay, now we have some buzz. Celtic folk. This could be an interesting one. Witch house. This is not my app, by the way. This is Google Labs. If you go Google Labs, labs.google, you have the flow there as well. The new VO3 should be there. VO3, yeah, we generated quite a few VO3 things. Yeah, they didn't go very well. They didn't do really well.
Real data is like a wild ride, but synthetic is a controlled party, often better for learning the basics without the craziness. Throw
Yes.
all your funny biomedical wearables into the bin and start
that's right.
generating synthetic data.
Yeah, that's right. I love this one. Throw all your biomedical data.
Throw all your funny biomedical wearables into the bin and start generating synthetic data.
Love this one.
Who needs those pesky wearables anymore? With this synthetic data, we're unlocking breakthroughs at the speed of light.
Yeah, love it. What else should we generate? Yeah, feels like future's already here. Yeah, that's right. What else did we have? We had another one. Don't remember this one. Yeah, it's all a bit broken. It's all a bit broken. This one will actually stop playing after some time. I don't know if you need to refresh it. Okay, it's actually pretty annoying. Yeah, it's not doing really well today, is it? It's not doing really well today. Okay, now we're talking. Anyhow, so we reviewed those. Did we have any? Yeah, so the site. Go check out the site. Let me know what you think. Any specific questions, excluding what is this? I'm more than welcome. Do we have camera connected? No, we don't have a camera connected, so we can't try some of these tools, but you can try them yourself. Try them yourself. You'll love this one. Alright, so yeah, Gemini. Guess we gave all the JSON file to Gemini. It's generating a lot. It's very keen. Yeah, we can listen to it, but we would not, because it's probably not very useful, not very conversational. This we can pop it into Notebook LM. There's no humans who wants to chat. Can we just give it the whole lot? Just do text real quick. Well, it's essentially like the same as reading this out loud with a text-to-speech, except it becomes way more conversational. So it's doing this generic stuff. Can focus, or just focus on the problems, be critical. Dark humor is fine as well. Just do default length. Let's see what we get. Essentially, I can't be bothered reading it. Oops, what's it thinking? What was that? Sometimes it would just stop playing whatsoever. I think I got too many things going on. Did the Notebook LM finish generating? No. Still just memory, 500 megabytes in memory. That's quite a bit. Yeah, it's not responsive. That's Google Labs for you. Google Labs. Hopefully our tool's working a bit better. Yes, one of the recent ones we have this cochlear implant simulator. It's actually not working well on a touchscreen. Well, I wasn't designing it for a touchscreen, but then you would kind of think it would just work, but no, it did not. So you can move it around and go play with this one as well. can move it around and see how a cochlear implant is being inserted into the inner ear, into the cochlea. I did a PhD on this stuff, so. But yes, what is it? Gemini, probably. It's probably Gemini and Claude did this one together. So they know quite a bit, yeah. So if you are doing some generic data stuff, yeah, start searching for jobs. Flipping burgers or something, because this thing will definitely be taking your job.
Welcome back to the deep dive. Today, we're taking a close look at some really specific materials you sent us. It's excerpts about a cochlear implant insertion simulator.
That's right. We're going deep into the technical side of what sounds like an interactive web app.
Yeah, an app designed to simulate something incredibly delicate, inserting the electrode array during cochlear implant surgery.
Exactly. And it's a really crucial step in that whole process.
So our mission here, just using the source material provided, is to unpack the technical features, the parameters it tracks, and what this simulator is actually for.
Mm-hmm. And the source reminds us the core idea of a cochlear implant is helping folks with profound deafness by electrically stimulating the auditory nerve.
Right. And this simulator focuses purely on getting that tiny electrode array safely into the cochlea, the inner ear structure.
And the source gives us a couple of tech hints straight off. It mentions 3JS.
For the 3D rendering, right. So you can actually see the cochlea model and the array.
Precisely. And also chart.js, that suggests data visualization.
Yeah. Okay, so displaying measurements, graphs, that sort of thing.
That's the idea. So fundamentally, it's an educational tool.
Yeah, letting someone, virtually try out and understand the mechanics, the forces, the key numbers involved in this very specific surgical action. Let's maybe start with how you actually interact with it.
Okay, so the main way you interact, according to the source, seems pretty intuitive for this kind of simulation. You click and drag.
Click and drag where?
Vertically. Either on the metallic electrode rings themselves or on the clear silicone carrier holding them.
And dragging down inserts it further.
Yep, simulates insertion. Dragging up simulates retraction. Pulling it back out. Makes sense.
And when you're not dragging the array, I assume you can look around.
Exactly. Standard 3D controls kick in then. The source mentions orbiting the view with the left mouse button.
Okay, spinning around the model.
Panning side to side with the right button or a 2-finger drag.
Shifting the view.
And zooming in or out with the mouse wheel or a pinch gesture. Pretty standard for 3D viewing, essential for checking things out properly.
Absolutely.
Yeah.
But the really core technical part seems to be the feedback it gives you, right? The numbers.
Oh, definitely. The source calls it a HUD, a heads-up display, usually top right corner, it says.
And that's showing the critical data in real time, like what specifically?
2 key things mentioned, depth and force.
Okay, depth measured in millimeters.
Millimeters, yes, very precise. And force measured in millinewtons.
Millinewtons, wow, that's a tiny unit of force.
It really is, and that's crucial. It highlights the extreme delicacy needed. A millinewton is like barely anything. The force of a tiny water droplet, maybe?
So tracking force at that level tells you just how fragile the cochlea is.
Exactly. And the HUD doesn't just show numbers. The source says it uses color-coded messages, too.
Like warning signals.
Kind of. Messages like safe to insert when things are okay, but also warnings if you, say, exceed a certain force threshold.
A threshold mentioned in the source, implying risk.
Yes, implying risk of, potential tissue damage inside the cochlea. It directly links your action, quantified by that MN number, to a safety outcome.
So it's making the abstract idea of being gentle very concrete. You see the number, you see the warning. It's direct technical feedback.
Precisely. It's not just about the movement. It's quantifying the interaction forces at a micro level. Very technical.
And it doesn't just give you that live feedback, right? It tracks your whole attempt.
Correct. There's also an insertion metrics chart, typically top left, according to the source. That's where chart.js comes in.
So that plots the data over time.
Yeah, it plots depth, force, and also speed throughout your insertion attempt. You can apparently resize or collapse it.
So you look back and see exactly when things went wrong, or
Right.
see where the force spiked.
Exactly. It provides that historical context to your actions.
Yeah.
Really useful for learning. You can see the trends, the correlations between speed, force, depth, and those warnings.
It's like a data log of your dexterity. Or maybe lack of it. The source also mentions a play pause button.
Ah, yes, for automated insertion sequences. Probably helpful for showing an ideal insertion, maybe different scenarios.
Right, so you can compare your attempt to a perfect run.
It seems like it.
Yeah.
So you put all these technical pieces together, the specific drag control, the 3D view manipulation, the real-time HUD with milNEM and MN, the safety warnings tied to force thresholds, the historical chart.
It all paints a picture of a tool designed to really emphasize the link between technical execution speed, force, depth, and a safe outcome.
Definitely. It underlines how crucial precision is and how exceeding limits, even by tiny amounts measured in millinewtons, has potential consequences. It's about understanding the numbers.
So stepping back, this deep dives into the simulator's technical guts, built with tools like 3.js and chart.js, really highlights the complexity. It's not just about steady hands, it's about responding to precise technical data.
Yeah, it really drives home the level of technical precision involved in modern medical procedures, making something complex, quantifiable, and trainable.
Which kind of leaves us with a thought for you, the listener. This simulator trains users on staying below a specific force threshold measured in millinewtons to avoid damage. So how might that idea, the concept of a critical safe threshold defined by specific numbers and units, apply to precision tasks you deal with, maybe in your work, hobbies, engineering, art, even just, delicate everyday things?
And how does actually knowing those precise numbers, the MN, the immer, change how you approach that test compared to just sort of vaguely being careful?
Yeah.
That's something to think about.
That's right, something to think about or try it out as well. You can go BioniChaos.com/cochlea insertion and try it yourself. If your parents wanted you to be a surgeon, a neurosurgeon, an ENT surgeon, or any surgeon, this is your opportunity. Then after using this tool, you can tell your parents, hey, I'm now a surgeon. Well, at least the virtual one. And if you are able to insert the cochlear implant without causing damage like this, then you get a certificate from BioniChaos.com. You can put it on your CV. But yeah, good luck. You can actually try and see if you can win AI. Probably not in real life, but in this procedural animation game, you do have a chance. All you need to do is eat that AI lizard or starve it to death. Which one will happen first? Which one will happen first? Okay, I'm getting slower, bigger, and slower. Can I? Will I get stuck in there? Now this YouTube channel might turn into a game streaming. Hopefully not. Hopefully not. Anyway, try it out, see if you can win AI. Will AI eat you? Probably will. But don't give up. Don't give up. Keep going. Might get stuck. Get stuck? Oh, I will get stuck. Yeah, I ate AI. Can you win AI? Yeah. So you can. Someone actually told me they hate this game because they couldn't win. So there you go. It is hard, but never give up. Never give up. And yeah, go check out the website. Let me know what you think. We have a lot more tools coming up. Did it actually follow instructions? We told it to focus on the problems. Yeah, we're looking at this interactive 3D brain mapping visualizer.
All right, welcome. Today we're diving into some absolutely fascinating and, well, sometimes, frankly, unsettling material you've shared.
Yeah, it's quite the collection.
It's a set of notes and research all focused on, how glitches in the brain's hardware can manifest as really bizarre clinical symptoms.
Mm-hmm.
Our mission for this deep dive is pretty straightforward.
Mm.
We want to try and connect some truly strange experiences. People report things you might not even think are brain-related directly to specific areas up there. We'll use your source material as our guide.
And I think it's really key to say upfront, while textbooks often give you these neat diagrams, brain area A causes symptom B.
Right, nice and clean.
Exactly. The reality, and your sources really hammer this home, is just far, far messier. So we're definitely going to spend a good chunk of time exploring the challenges, the complexities, the real problems in actually applying this knowledge. Because, yeah, the brain isn't always a simple machine. Totally. So think of this as understanding the mechanics, maybe the disturbing mechanics sometimes, behind what happens when the brain goes wrong. We'll look at those textbook links first, the ones from the source material.
The classic connections.
And then we'll kind of pick them apart a bit, just like your sources suggest we should. Okay, let's get into it.
Sounds good.
So the basic idea that the sources lay out is that the brain isn't just, one big lump. It's got specialized areas, each doing its own job.
Highly specialized, yeah.
And when activity goes wonky in one area, like during a seizure, for example, it doesn't just shut down. It can actually produce very specific outputs, weird outputs that we experience as symptoms.
That's a great way to put it. The scenarios in the material often link these unusual symptoms directly to areas having abnormal electrical activity, like seizures.
Yeah.
It's almost like finding the specific wire that's short-circuiting.
And seeing what weird signal it blasts out.
Okay, let's jump into some of those strange perceptions and feelings your sources mention, like déjà vu, that really intense, unsettling feeling that you've experienced something totally new before.
Uh-huh. We've all had mild versions, maybe.
Right, but this is different. And sometimes the source even pairs that with involuntary stuff, like lip smacking. How on earth does the brain produce that combo?
Well, this is where it gets fascinating because it's specific but also complex. The source links that intense déjà vu feeling directly to abnormal activity in the temporal lobe.
Okay.
This part of the brain is super involved in memory processing and emotion, too. So when seizure activity hits certain spots in the temporal lobe, like the inferior and middle temporal gyri mentioned,
Right.
it can basically hijack the brain's familiarity signal. It flips the switch that says you've been here before, even when you haven't, creates that really strong, false sense of recognition.
Wow. Okay. And the lip smacking.
Ah, the lip smacking. The source calls it an oro-elementary automatism. Bit of a mouthful.
Yeah, sounds it.
But it's basically one of those common, involuntary, repetitive movements you can see in temporal lobe seizures. It seems like the seizure activity grabs hold of these really basic, almost instinctual motor programs stored in that area, things related to eating, chewing, swallowing.
Primitive stuff?
Exactly, and it just plays them out automatically, involuntarily. So the brain's core wiring is sort of briefly misfiring in a very specific way.
Okay, so false familiarity and weird chewing, both potentially from the temporal lobe. Makes a spooky kind of sense.
Oh.
What about seeing things that aren't their visual hallucinations, and then that gets paired with the sudden, intense fear? They don't seem obviously connected.
No, not intuitively. And this starts to show us how different brain areas can get tangled up together. Your source links visual hallucinations, seeing lights, patterns, even complex scenes that aren't real to the occipital lobe.
Back of the head, the vision center.
Precisely. The visual processing hub. Dysfunction there, maybe from seizure activity in places like the middle occipital gyrus or other areas mentioned, directly messes with your visual input. It can literally create images from nothing.
Okay, that explains the seeing things part. But the fear,
Right, the sudden, overwhelming, unprovoked fear, the source attributes that very strongly to the amygdala.
the fear center.
Yeah, that little almond-shaped structure deep inside the temporal lobe, actually. It's the brain's main threat detector. When that gets abnormally stimulated, maybe by spreading seizure activity, it triggers pure, intense terror, completely out of context.
So the seizure could hit the visual area and the amygdala.
Exactly, or spread from one to the other very quickly. So you end up with this horrible experience, seeing something terrifying that isn't real while also feeling absolutely gripped by inexplicable fear. It's a nasty combo born from specific brain spots misfiring together.
Yikes, okay. Seeing scary things, feeling terrified. Occipital lobe, amygdala. Got it. What about hearing things? Auditory hallucination sounds, voices maybe with involuntary head turning.
Okay, so auditory hallucinations, hearing things that aren't there, the source links that to the superior or upper part of the temporal lobe. That's where your primary auditorial cortex is located.
Makes sense. Hearing center.
Right. Abnormal activity there, maybe in the planum polaire or middle temporal gyrus for more complex processing, makes the brain think it's hearing sounds or voices.
And the head turning.
The head turning, what the source calls a aversive movement, that's a motor sign. It usually means the seizure activity isn't staying put.
It's spreading.
It's spreading. Often it's moving from where it started, maybe that temporal lobe spot causing the hallucination, across the brain to motor control areas on the opposite side of the contralateral hemisphere.
Okay.
And when it hits those specific areas controlling head and eye movement, it forces the head to turn, often towards or away from the side the seizure started on.
It really is like tracking a storm moving through the brain's different neighborhoods. Okay, let's switch gears a bit. Movement and sensation symptoms, the brain directly messing with the body. Like muscles suddenly going rigid, then maybe the arms start jerking rhythmically. It sounds very physical.
It is, very much so. Your source connects that specific pattern, the initial stiffening, which is called the tonic phase, followed by the rhythmic jerking, the clonic phase, directly to the primary motor cortex.
The command center for movement.
Exactly. That crucial strip in the precentral gyrus, it sends out the signals for voluntary movement.
So what happens during a seizure there?
Well, the seizure activity is basically like chaotic, overwhelming noise flooding the command center. It sends out these haywire signals to the muscles. The initial massive discharge causes the muscles to contract all at once, really rigidly. That's the tonic part. Then, as the seizure activity fluctuates, becoming more rhythmic in its abnormal firing, the signals to the muscles become intermittent. That causes the muscles to repeatedly contract and relax the jerking or clonic phase. It's a direct physical manifestation of the electrical storm in the motor cortex.
Direct link.
Uh-huh.
Motor cortex chaos equals body spasms. Makes sense. What about problems with coordination? Feeling clumsy, unsteady, poor balance.
Coordination and balance. The main player here, according to the source, is the cerebellum.
Back and bottom of the brain.
That's the one. It's absolutely vital for fine-tuning our movements, keeping us upright, making sure everything is smooth and coordinated. Damage or dysfunction there leads to ataxia, that classic clumsiness, unsteadiness, difficulty with precise actions.
Okay.
Your source also adds that other areas chip in, particularly in the parietal lobe, like the superior parietal lobule. These parts help integrate sensory information, knowing where your limbs are in space, for instance.
Right, body awareness.
Which is information the cerebellum needs to guide movement accurately. So it's mainly the cerebellum, but it relies on input from these parietal areas too.
Cerebellum for balance, parietal for body sense.
Mm.
Got it. Now here's a really weird combo from the source. Suddenly losing vision and at the same time feeling numb down one side of the body. Those seem like totally separate issues. Why would they happen together?
Yeah, that is a strange one, and it really highlights how physically connected brain areas are and how seizures can spread along specific routes. So sudden vision loss, like we talked about, points to the visual pathways, probably the occipital lobe.
Okay, vision again.
Right, and the numbness or altered sensation that points to the parietal lobe, specifically the primary somatosensory cortex there. That's the brain's receiving station for touch, temperature, pain from the body.
So vision area, body feeling area, how do they connect?
The source suggests this combo can happen if seizure activity starts, say, in the visual part of the occipital lobe and then just spreads forwards. It moves right into the adjacent sensory processing areas in the parietal lobe.
Like wildfire jumping a boundary.
Kind of, yeah. The abnormal electrical storm just sweeps from the vision processing region straight into the touch processing region, causing both symptoms to appear almost simultaneously, even though they originate in different but neighboring functional sounds.
Wow. Okay.
Anyhow, we will continue this next time. Let me know if there's any questions. Yes, there is a human in the loop. Go check out the website, like, subscribe, share if you're with anyone who might be interested. You know what to do. And I'll address any further issues next time. See you in a bit. Bye.